We normally build a dam to hold water back and store it for use in water supply, irrigation, hydropower, or flood control. But sometimes we have to let some water go. Whether we need it downstream or the impounded water behind the dam is simply too full to store anymore, nearly every dam needs a spillway to safely discharge water. Hey, I'm Grady, and this is Practical Engineering. On today's episode, we're talking about spillways. This episode is sponsored by Skillshare. More on that later. To understand spillways, we first have to understand hydrology. More specifically, we have to understand the tremendous variability in inflows that can affect dams and reservoirs. Designing a dam would be simple if rainfall and snowmelt were consistent throughout the year. In fact, most dams wouldn't even be necessary, since hydrologic variability is the reason why most dams exist in the first place, to provide storage of water and smooth out the ebbs and spikes of inflows to protect us from flooding or so that the water can be used to meet our needs throughout the year. But those spikes in inflow can be enormous. It's not unusual for a watershed to generate the majority of its entire annual volume of water in a single storm event. Those inflows can reach a reservoir with very little warning, so dams need to always be ready to handle major storm events. As far as infrastructure goes, dams are fairly risky. Depending on the size of the structure and what's downstream, the failure of a dam can be catastrophic. In fact, some of the worst human-caused disasters in history have been failures of dams. For this reason, they're often required to withstand the biggest storm that we could possibly conceive, called the probable maximum flood. It's too expensive to build a dam so tall that it can store the entirety of this flood. On the other hand, we can't just let the flood overtop the dam, because flowing water can damage and destroy the structure. So in most cases, dams are designed with at least one spillway, a structure that can safely discharge floodwaters without causing injury or deterioration to the dam. The water stored behind a dam is called its reservoir, and the term spillway is usually reserved for a structure that releases excess inflows when the reservoir is already full. For example, a big flood or heavy snowmelt. This distinguishes spillways from other structures that provide releases from reservoirs like intakes that serve pump stations and penstocks that serve hydro turbines. Because of the variability in inflows, many large dams have two or more spillways. The smaller one is called a principal or service spillway that passes normal inflows when the reservoir is full, and the other one is called the auxiliary or emergency spillway that only engages during extreme events. Depending on the design, the auxiliary spillway may only flow for a few scary moments in a dam's entire lifetime. Because of that, they can be as simple as an excavated channel cut around the dam. It might not last very long, but it can protect the dam from failure in an extreme situation and be repaired afterwards. No matter how often it flows, a spillway has three main jobs, and there is a wide variety of structures that can accomplish these objectives. But I think if you're going to demonstrate a spillway on the internet, there's only one obvious choice for the model: the morning glory. This is a type of drop shaft spillway that has enchanted the internet with crazy vortex photos, and I built a model of one here in my shop so we can use it to discuss the basic functions of a spillway. And the first basic function is the most obvious, to manage the water level in a reservoir. A morning glory is in a class of spillways we call uncontrolled. In general, they're set and forget. There are no gates or moving parts to manage. They regulate the reservoir simply by existing. If it gets too high, the water flows out and the pool goes down. If the pool is below the crest, no water is released and the level goes up as precipitation makes its way into the reservoir. Most uncontrolled spillways are weirs, which I covered more in a previous video. A weir is simply a structure that allows water to pass over its crest. The morning glory acts like a circular weir at first, but as the water level goes up, the bell mouth chokes and the behavior changes. This type of spillway is used in narrow canyons where there isn't much room for a more conventional overflow. Uncontrolled spillways normally need to be pretty big to handle even the largest storms that a reservoir might face without any moving parts. That can get expensive quick, so an alternative can be to use controlled spillways with different types of gates. The gates add complexity to a spillway, but they can also reduce its cost by providing flexibility and discharge capacity, allowing for a smaller overall structure. The gates can be operated to match the size of any storm event, even if the spillway is relatively small. The next job of a spillway is to safely convey flow to the downstream side of a dam. In most spillways, including my model, water has to make its way from the top of the reservoir to a natural watercourse downstream of the dam. That's often a big drop in elevation, which means the water can pick up a lot of speed. This high-velocity flow can cause major damage, so we need some way to contain it safely. Sometimes it's a pipe or a conduit, like in my model drop shaft spillway, and for open channel spillways, it's called a chute. A chute also needs training walls on the sides to keep the flow contained. Both spillway conduits and chutes are often made of concrete because it's one of the only materials strong enough to resist the damaging forces of the high-velocity flow. That leads me to the final objective of a spillway, energy dissipation. I mentioned that all the water moving so quickly can cause serious erosion downstream of a dam. If not controlled, this erosion can progress upstream, eventually leading to failure of the dam. So all spillways need a way to dissipate hydraulic energy and slow down the flow before releasing it into a natural watercourse. For large spillways, this is often accomplished in a structure called a stilling basin that forces a hydraulic jump to occur. This is another topic I covered in a previous video, so check that out if you want to learn more. For smaller spillways, the dissipation can be simpler, like rock riprap, or even just letting the flow plunge into a deep pool like I'm doing here in my garage. Once most of the hydraulic energy is lost, the water can safely travel downstream without causing damage. Like most of my videos, I'm just scratching the surface of a gigantic topic. The spillway is a critical part of any dam and often the most complex component. Designing a spillway usually requires a team of engineers performing structural, geotechnical, electrical, mechanical, hydrologic, and hydraulic analysis to get it right. Also, we can safely discharge water from a reservoir during a high inflow event when there's no more room to store it.
In this video, we will see about canal regulatory works. Especially, we will see about canal falls and canal escapes in detail. So, what is canal regulatory work? It is nothing but when a canal is there, you provide some regulation work so that you can control the amount of water passing into it. So, some sort of how you control everything. So, that comes under regulatory canal works. So first we will see about drops or falls. So the whole aim of drops or falls, it is provided to lower the water level of channel. So what happens is sometimes you have a constant bed slope, but in some areas the terrain is totally different. So you have a constant bed slope which is sloping down and water is passing. Then suddenly you have a huge drop where the slope is greater than the bed slope. So this slope greater than the bed slope. So what happens is water kind of speeds up here. So the velocity is very high and again you have normal slope. But because of this fall, there is extra energy because of which the velocity goes high, which is an obvious fact. So because of this velocity, lot of erosion takes place. So this sort of erosion or scouring is not good for the canal. So that is when falls are provided. So what you do is you artificially destroy the surplus energy, which otherwise will score the bed. So that is the whole idea of this falls. We'll see more about it in the next slides. So other regulation structure is cross regulator. So what happens is sometimes when you have a canal here and you need to divert the water this side for some irrigation works, what you do is you head up some water here by building obstruction. You make this water level go high, then direct it via some offtake channel. So that's called offtake channel where you direct it. So to regulate this, you have a cross regulator, and this distributory regulator is to control the amount of water going inside this offtake channel. Then you have escape. Sometimes what happens is if suppose a lot of rain comes or some other condition because of which excess water comes, then this offtake channel will have very high water, or even the canal will have very high water supply. So if it goes above the full supply level, it will go above the canal and then start eroding the bed, which is undesirable. So in that case, you release some of the excess water from the canal. That is known as escape. What are the design requirements for canal falls? So when you artificially provide a jump like this, so let us say water is going here and suddenly you provide a fall like this. So what happens is water goes down with huge energy. So this downstream portion, which I am representing as D bar S, and this is upstream portion. So from the upstream portion, when the water flows down to the downstream, here this lot of energy will start eroding the bed, which is again undesirable. So the downstream portion should be safe against erosion. And for that, what you have to do is you have to control this velocity. If this velocity is very low, approach velocity is very low, it might not erode the bed. So other design requirement is that approach velocity should be minimum. So how is the site selected? The site is totally selected by economic considerations. Sometimes you have to work out the benefits between the cost of fall and balancing earthworks to make the bed slope in the uniform condition. That is fill and excavation. So site is depending upon the economic considerations. Now let us see the different types of falls. So first we'll start with something called the OG fall. It is a very olden fall, like it was used in the olden days mostly, where it consists of convex and concave case, as you see in this image. So here no crest is provided. So water simply goes and then there is a curve where the curve is provided where the water falls. So because no crest is provided and here there is a slope down, there is heavy drawdown on the upstream, that is water is pulled down, because of which the approach velocity will be very high and it will start eroding the beds. So later on what they did was they tried raising the crest so that the approach velocity will be little lesser than what you find here. So the second type of falls is rapid fall. Even stepped fall is similar to rapid falls. So here a lot of falls are provided, like suddenly it's gonna dissipate energy by turbulent diffusion mostly. So this is a very effective method, but it is very costly, hence not used. Stepped fall is also similar to rapid fall, where you have lot of steps like this. So instead of providing a single fall like this, you provide it in steps, which is more effective. And again, like rapid fall, it is very effective, but again it's costly. So it's not adopted that much. So the other type of falls is trapezoidal notch fall. So as you can see from both of these images, there is constant depth discharge. Like here, because some trapezoidal structures are provided, the depth of this does not increase. Like when you provide a crest like this, water level increases. But here the depth is constant. How much ever water was flowing, it will just go down. So there is no drawdown on the upstream side. There is normal water depth. It's known as constant depth discharge. The other type of falls is siphon, well drop or well type falls. So what happens is here a well kind of structure is provided. Let us say water is flowing. So what you do is you direct everything through a small pipe kind of structure which falls into a well. Let us say this is the well, and here water falls. So here water falls with huge energy, and all this energy is dissipated by turbulence inside the well, like water keeps on mixing with huge power. Then you provide another structure outlet for the water. So water comes inside like this, drops into the well, lot of energy is dissipated by turbulence, and then the water comes out. So in this way, water is dissipated, water energy is dissipated inside the well itself. So this is mostly used for very low discharges because you have to direct it through a pipe. So it is used for low discharges, and when you have to drop it through a huge amount. And hence it is mostly used for tail escapes for small channels. Like we saw about escapes. So this kind of thing is provided. So in order to destroy the extra energy. So this is a very modern type of fall. It's known as the vertical drop fall, and it is also known as Sardar type fall. It is a canal in UP, Uttar Pradesh. So this kind of fall is a modern fall which is mostly used nowadays. So what happens here is you provide a crest here. So the water, there will be some drawdown. Water level will rise. The approach velocity is little minimum because you provide a crest. And then what you do is you provide a depressed floor. So if you see, the height of this is greater than height of this area. So you provide a very depressed floor. When you provide a depressed floor, what happens is there is some sort of cushion sort of effect. So when water falls, there's a cushion sort of effect where energy is released by turbulent diffusion. Sometimes what they do is in this area, they also provide some friction blocks, which will again help in dissipating the energy in a better way. Like in the end, turbulent diffusion happens and then the excess energy is dissipated. So these are the different kind of canal falls. Now let us see about canal escape. So what we saw was when water flows down the canal, sometimes when excess water is there, you let it down, go through an escape. So this happens mainly because due to high rainfall or wrongful operation of headwork. Sometimes you release too much water. So if this is not provided, the water level goes above the full supply level, which is very dangerous. If this is the full supply level, if water goes above the banks, it will start eroding and all that. Lot of ill effects happen. What you do is you provide canal escapes. So if this is the canal and water is going like this, you provide a weir just above the canal bed level so that water will escape here, and some stone pitching and all that to release the energy in a better way. Sometimes even you provide like gates, sluice gates. So either you provide weir type or sluice gate types where you have gates which you can open when there is surplus water alone and water will flow out. Thanks guys for watching the video.